and welcome back to Differential Equations Show, section 2.3 on acceleration and velocity models. So we're going to derive some of the formulas you have seen in physics courses. You will know where they are coming from. The cheapest, fastest, easiest one, obviously, is the basic parabolic motion, where we understand that anything you throw on the planet, well, if you don't throw it way too fast, meaning escape velocity and so on, so anything you throw will fall back onto the surface of the Earth because of the pull of gravity. So the weight of an object is its mass times acceleration of gravity, and the force of the weight, right, which is the force, is in gravitational field going to be attracted to the planet because gravitational force is always attractive, and being that the planet is way bigger than a rock or something you want to throw, we perceive that rock falls down, even though in reality rock does fall down and the planet proportionally climbs up a little bit. So that's that's something you can definitely compute, but you cannot measure or something because the calculation should be off of the order of more than 10 to the 30th, negative 30th, sorry. So that's like at least 30 zeros before you start getting numbers. Anyway, in terms of motion. So what are we going to do? Well, we're going to understand that when you throw something at whatever angle, it will eventually hit the ground, and it covers some distance forward in time, and it also has some height, which is height y, and we can call this one over here y max, which is the maximum height at a certain time. Call it T max or TM, whatever. Now, as I said, everything that you toss will fall with gravity. Therefore, our acceleration is going to be g. And because we are in physics, we're going to say negative g because it is going to go down from our reference point, right? Because we are stuck at the planet. So because we are stuck at a planet, we're just going to observe that as a negative g. So now you're going to say that acceleration equals negative g, and as we did before in calculus 2 and so on, we'll say that acceleration is a change of velocity, right? So change in velocity in time equals to negative g. Now this negative g, g is given as 9.81 meters per second squared if you're using metric system. G equals 32.2 feet per second squared if you are using imperial system. Those are the numbers that you should know because you're just alive, right? That's pretty much the only requirement. Now we do the separation of variables, right? So we have dv equals negative g dt. We hit both sides with the integral. You can actually keep g outside, that's a constant. And we're going to have that the velocity is equal to negative gt plus some constant c. Now this c we are going to call initial velocity. Because at time 0, velocity equals c, so initial velocity is there. There is a difference whether you drop something, right? When you drop something, then it had no initial velocity. It goes straight down. But if you slam something, this motion, while you're still holding it in a hand, while you're slamming it to the floor, right? that is the initial velocity. So when you let go, even if you let go at the same height, the object will move faster because it will still be accelerated later on with gravity, but it had the velocity, initial velocity. So that plus c is actually initial velocity, which is a difference between dropping something or slamming it into the ground, right? So now we get to our equation where velocity as a function of time is equal to negative gt plus v0. Now, you might know this formula from your physics as velocity final is equal to velocity initial plus acceleration times time. You might have remembered that formula from your, right? And now your acceleration is negative g because it goes down, right? So you get the same equation. Some of you have velocity final, velocity initial on the same side, so you have vf minus vi and whatever you have. But maybe you used v0 instead of vi, whatever. So, but that's that formula from physics. And now we have equation for velocity, and then we take one more derivative. Not derivative here. We take one more separation of variables, because velocity is change of position in time. Yes, very good. Change of position in time. And the reason why I'm using y is because this is a vertical motion, right? The object goes up and down. Generally in physics, they would use either d or s, right, for distance. But this one is the vertical one because we're talking about parabolic motion. Therefore, we'll do this. And then your dy is equal to negative gt plus v0 in parentheses dt, because dt has to multiply everything. We integrate both sides because we did separation of variables. And then you have your height y equal to negative gt squared over 2 plus v0t plus y0. And this equation is remembered as negative 1/2 gt squared plus plus c, because when you integrate, and then we'll say that c is initial height. All right. So now, when you integrate, you get plus c, then you define that plus c to be initial height, and then you write the equation. So this is the equation you memorize in physics, and this is the equation you memorize in physics. So these are the two equations you memorize in physics. One gives you the height as a function of time. The gravity is going to be the constant, and it's different for a different size planet, right? You have difference also for the moon and the Mars, right? They're all way smaller than Earth. Earth is way smaller than the sun, for instance, even though you wouldn't be walking on the sun to feel a gravitational pull, but still. The trick is that when you launch something from the Earth, it has to battle the atmosphere we have, right? Because there is it's harder to go through the air. And then it also has to battle the gravity. It takes way less thrust to lift something off of the moon, and more, obviously, from Mars. But still, both of those less than the Earth to propel back, right? Because has less resistance to go back. So now you can see what are the components for something to, this is a parabolic motion. So if you are designing something and it's going to fit within this equation, right, well, it's not going to escape, right, the gravitational pull. So I have to be careful about that. You see that time is a factor. initial velocity is a factor, right? And then obviously the height from which you throw. If you think about the basketball, right, and you have the hoop at some height, you definitely want taller people to play it because they will be closer to the hoop than the shorter people, even though shorter people generally are faster to move around. So the mix is good, I guess, in a team. So you have the y0, that's the factor in how high the object is going to reach, and obviously v0, how far you fire it, right, in terms of initial velocity, which could be 0. If you drop an object, then v0 is just 0. Another thing that is very important is dimensional analysis, making sure that all of these terms which are added have the same units. That's also extremely important. You cannot just put the formula together and say, yeah, this is good, right? The units have to make sense. The units have to all align. And if they are not aligning, then obviously you have an issue. The formula is definitely not correct and useless in physics if the units do not add up. The units of, in this case, would be, let's say, feet for y, and then you have 1/2, no one cares. G would be feet per second squared, and then here's your time in time squared, and they cancel. And then you would add feet per second, but then times single t, and then that cancels, right? And then plus another feet, so you have feet plus feet plus feet equal feet. So this is called dimensional analysis, and it's one thing that it's very important for every physics formula. I just hope that physics professors do this for every single formula you ever see in physics. Otherwise, you can get some really, really bad results. I'm just going to put this on a side and then ask you to eventually go and try and figure out things. E equals mc squared. Would those units add up? Right? Because all of a sudden we have energy and mass and velocity on a pile. They make, right, no sense mushed together. But once you do dimensional analysis, you will see that it's dimensionally perfectly sound. And of course it works. I mean, we measure it many times. We have a lot of devices that work on basis of this formula. TV and GPS being like two of those that are, well, old TV. The one with the, not the LCDs now, the one with those electron tubes, cathodes, right? Those TVs use this formula. And then your GPS and a whole bunch of other stuff works because this was figured out. And what else can we do? Kinetic energy. What was that? 1/2, I heard it. mv squared. That's the same equation, isn't it? Oh, okay. It's just little different numbers, right? Okay, cool. So this is how you do physics, right? You make sure that the units all line up. You have the potential energy one with mgh, make sure that works out. And then you convert one into another, keeping the energy constant. Since you can convert mass energy, right? You can add that system in and have everything on a pile and compute some really, really cool things. So keep in mind dimensional analysis and try these things on your own. All right, cool. So now, if we want to figure out y max, right, all we need to do is to set velocity equal to 0 in v equals v0 minus gt, because, right, clearly velocity equals 0 means that it's the maximum point, every object that you throw and falls back to the ground has to stop at the highest point. So from there you can get time. Then use, let's use y equation to get y max, and that's it. So to get y maximum, this is the same problem you guys had in Calc 2 and Calc 3. Those of you who took, I know that not many of you took Calc 3 yet, or you're taking it right now, but if you did Calc 3, same problem was there as well. Cool. Now, we are also going to take a look at some more physics, and we're going to take a look at the equation for force due to gravity when the object is close to a planet, right? There is the gravitational pull between two objects. Every two physical bodies, doesn't matter how big, doesn't matter how small, they exert gravitational attraction towards each other. Now, the reason why we don't simply like stick all together, all 40 of us on a pile, right, once we get to close proximity, is because the gravitational force drops off with a square of distance. That is the gravity is the weakest, right? It's the weakest of all forces. It's very easy to beat gravity, right? If you ever lifted anything, anytime you lift, you beat gravity, right? Because gravity is pulling the other way. You were not always able to get the magnet off of the fridge easily, right? Especially, right, with some stronger magnets. And some of these cases before had magnets that when they fall off and they stay glued to this, we couldn't pry them off with anything we tried, right? This big, right? You can lift it, but you can't get it off because it's magnetic, right? So magnetic electrical forces are much stronger than gravity, and those are actually nothing when you compare them to nuclear forces that keep atoms together and molecules together and so on. So that's pretty much where we are. So now we're going to say that force due to gravity is going to be, well, let me just put, actually first, before I do that, let me just write in the parentheses F equals ma. That's the famous Newton's equation, right? The force, that's what he observed when he got hit by an apple, and then, I guess, I don't know how that works, but yeah, apparently what that is supposed to promote, that you should repeatedly hit yourself in the head with something, right, until you learn things. I don't know. Did it ever work for anyone? No, obviously not, right? So the story is not true, but hey, it's a cute story. Yeah, I know, you take the chemistry book, right, or physics book, and you just keep slamming yourself into the head until you know all the formulas.
Definitely how it works.
Definitely, yeah.
That's the trick. Yeah.
Or when they tell you should sleep on the book, right, instead of the pillow. I guess so all of the knowledge kind of sucks up into your head. Don't do that either.
Yeah, sure.
It clearly doesn't work. Anyway, so force equals mass times acceleration, right? So when you have that one, you can say that the force due to gravity is going to be the mass, and then acceleration is dv dt, right? That's our acceleration. And we got ourselves a differential equation there, but also remember that force times gravity is going to be actually the weight, which is the negative mg, right? So we can plug in that one as well and figure out a whole bunch of things. Nice one. So
Wait, for the letter that's underneath the F, is that a G or an A?
G.
for Fg, yes, that's the force due to gravity, right? So that's why they put They put capital G. But then also that's the weight, right? That will be the weight. So you can do some differential equations here, right? Because you have a problem that has only one variable. You have the variable, you have the mass, you have velocity, you have the time. So you can do separation of variables and calculate stuff if you need to. Just want to see if I. All right. So now, so I'll just say this maybe blue. So. That's weight, right? It's weight. Usually in physics as W, right? Which is the mass times the gravity. And as I said, same mass, I'm going to be the same mass in kilograms no matter where I am. And on the moon, right, I'm the same mass, but the moon has much less gravity than Earth. So, oh yeah, Mike, you wrote that app for the cell phone that calculates your weight on the moon.
So you're telling
Do
me
I
if
still-
I want to lose weight, I should just go to the moon?
No, just if you want to feel good about. I don't know why less weight would make you feel good, but apparently, I should have it still. There it is.
No, I put it on your phone, yeah.
There it is.
Nice.
So let me see if I.
Yeah.
Yeah, I'm only 47 pounds on the moon. I mean, I technically don't exist. All right? You'd be able to fight me on the moon easily. But hold on, then you will all be like 13 pounds each, so never mind. Don't.
Gross.
Okay? Don't. Anyway, so we have the weight right there. And what I see here, what they did is they added the weight, the air resistance as well, right? We all know that if you toss a rock, it goes through the air, right, or something. But then you toss a leaf or a page of the paper, and it goes right like that. So air resistance is something else. Also with flying, you have the tailwind and the headwind, right? With the headwind, you are fighting against the wind, so the airplane is not going as fast as it could, which is why all of the arrival times on airports are always estimated. And sometimes you have someone over the ocean, right, traveling across the Atlantic or something, arrives 45 minutes earlier, and sometimes they're 3 hours late, right? It all depends on the headwind, tailwind, whether it's helping the airplane. It's also the currents, right, down the river, up the river, right, if you want to swim or a boat or whatever. So air resistance in this case when you have something, and we are going to call that one FR. So now we have FG, which is, let's do it here. And FR, force due to air resistance. And clearly it's going to be a negative force, right? Because it's preventing you from falling down. It's good in case you have a parachute, right? Air resistance is awesome, but if you're trying to launch a rocket, not so good, right? So I can get rid of this one over here. So now here is our new M dV dt is equal to Fg plus Fr. That's our new equation there. And the Fr equation, that's another side note here, is going to be given by k velocity to some power p. That's again something from Newton. He used the square. depends a lot of what kind of air you're going through, and also depends obviously on the speed. Generally, there are tables to pick these terms up. So for simplicity, we can use just negative kV. So our equation over here, where the resistance is proportional to velocity. So for resistance to be proportional to velocity, we need P equals to 1, which gives us that Fr is equal to just kV, and it should be negative kV because it's a resistance. So your friction force should be negative, your resistance should be negative, your gravity should be negative term in physics, because we do care about which way they're oriented, right? So now we have that our mass as dV dt is equal to negative mg and then minus kV. And that will be our equation, so that we can go and solve this using just a basic separation of variables. So now, how do we do separation of variables here? It's a lot of mess. Well, we divide first by what? By m, yes. We are going to divide everywhere by m. Now, you know what? I'm going to box this equation, and then I'm going to write this equation again and start solving it. This used to be on someone's project a couple of years back or something. I remember people stopping by, going crazy with the calculations, which is cool. All right, so divide by m everywhere. And now we have our dV dt equals negative g minus k over m v. Now, I have to follow the notation in a book, so I have to look. They're using a rho for this value here. So, rho is equal to k over m. Now, m is always a positive number because it's a mass. You cannot have negative mass. K was also a positive constant. So k over m is always positive, and when you plug in a positive number, it becomes a negative number altogether in the equation, right, when you combine it with the minus sign. But it's positive on its own. And the differential equation becomes dV dt equals to negative rho v minus g, if I want to follow exactly what they wrote. So now, we are supposed to solve this equation for v over here. So we have
Out of curiosity,
yes.
could you have just left the k over m in there and followed through with the k over m?
Yes.
Okay, so you didn't have to sub out.
You're writing one character instead of three.
Right?
I mean, there's a line. It's still a thing to write. In computer science, you do the same, right? Why do 3 characters if you can do 1? It's less memory, less everything. And so, plus you're going to have double fractions and all these kind of things to keep track of, especially if people don't line up things properly. It's just less mess. All right. So now, this is the calculation they don't do in your book. You're supposed to figure out. This. They just say equation 4 is a separable first-order differential equation, and solution is. Right? So technically, they give you one. Good luck, right? In between, and probably there is a homework assignment on it to do the separation of variables, right? To get to this point. So now you're supposed to work out your integral, right? And we do have a, dare I say, basic, right? ln over there on the left, and then we have to work out the solution in terms of exponential function, because you are expecting to get exponential function out of ln looking left side, right? So when we hit both sides with the integral sign, we can use the u substitution as negative rho v minus g. Du equals to negative rho dv. And I don't have negative rho, so I have to insert negative rho and put negative 1 over rho on the outside to battle the one I put in. And now, what do we have? We have negative 1 over rho integral. Negative rho dv is du divided by the whole denominator is u. On the other side, you just have t plus c, right, when you integrate. So now you have negative 1 over rho ln of u equals to t plus c. And we are going to move negative rho to the right-hand side. So the entire equation times negative rho. So we are getting our ln. U is negative rho v minus g equals to negative rho t. And I know you're going to get triggered, but such is life. I just put plus c because negative rho got absorbed by plus c. Plus c is this like the devourer of constants, right? You hit it, but times 2 and still stays c, right? So it's annoying. Anyway, so now all we need to do is to e both sides and just solve for v, and you are done, right? So just algebra left. So we're going to e both sides, and we're going to get negative rho v minus g equals to e to the negative rho t, and I'm just going to say times e to the c. Now that e to the c. Good. Now you will add g divided by rho. Divide by negative rho. So negative rho v is going to be, I'm just going to call this capital K now. E to the negative rho t. And there's going to be a plus g over here. And then we are going to divide by everywhere. Divide by negative rho. And get v equals, I'll just going to call it now capital M. E to the negative rho t minus g over rho. So they have this as solution. And M, which you can find if you use initial position of 0t. What happened?
But you have to sub back in rho. Rho is equal to k over.
Eventually, no, they left it as that, but we can, yeah. I mean, I'm going to do it. The book didn't do it. I am going to do it, but I still have to deal with them. So if you use initial condition, right, when you have the time equals 0 to figure out m, so if you start that at time equals v0 plus g over rho at velocity of time 0 is v0. So if you use this, and this 0 here means t equals 0, right? That's initial condition. So if you use that, in that equation, you will get that m is given by v0 plus g over rho, and this gives you the equation for velocity as v0 plus g over rho times e to the negative rho t minus g over rho. And now, we don't care about rho, right? We're going to put our k, which is our air resistance constant, right? And we're going to put our m, which is the mass of the object that it's falling or it's getting launched, right? So now we know that rho was given as k over m. Now this part is not in the book, but this is the full equation now. So v of t is equal to, this is v0. Please fix that. This is supposed to be v0. That one right there, v0, I dropped the zeros. So initial velocity plus, and now it should be gm or mg. Let's do mg. Mg over k e to the negative kt over m minus, and we have mg over k. And that's the model for the flight of the object. Hey, Rafael, come on in, man. Oh my God, for lunch? Sure, but come on, sit here. Yeah, class is over. Rafael is here, so. And he brought lunch. Oh my God. Anyway. Wait, did he really go? At least he can go sit upstairs. Give me a second. Where did he go?
Of course. Definitely.
Oh my God.
I would love it. No, what the fuck? Actually, I thought those didn't happen.
Yeah, it actually works. Now it's plus 2. So like 2, 3, 4, 5. 2, 3, 4, 5, 6, 10 through 8 is minus 1. The first time I went to casino doing this, it's not bad. I actually don't really know, but it took like 15 minutes.
He's fast. And all right. So now we have the equation. We have the equation, and we cannot have infinite velocity, right? There is every object falling with resistance has to hit the point where it cannot accelerate past that point. And for that we call terminal velocity. And for every situation, right, there is a terminal velocity. So think about, obviously, parachutes, right? When they compute, the size of the parachute, clearly, the larger the parachute, the more air will catch, right? The slower the person attached to the parachute will fall. But you have to be careful because that parachute has to safely unfold. The larger the parachute, the harder to unfold to its full extent, right? So you have to be careful and play the game, right? What is a maximum speed that the person can hit ground with and not break the bones, right? And you don't want to go and drop the person like a feather because the parachute might have to be like 4 times the size than it already is. So you have to be very careful in designing these kind of things, right? And that's where our terminal velocity, right? And the terminal velocity in this case is described by mg divided by k, where k is your constant of the air, right? So terminal velocity, or they call it terminal speed. It's terminal velocity because velocity is what? Speed, which is the magnitude, and direction, right? That's why it's velocity. We're going down, right? Everything is with terminal velocity is going down. Otherwise, it's escape, which goes up, right? So terminal speed is going to be given by velocity tau, right? That's the lowercase t in Greek, lowercase tau. And that's going to be our mg over k. And our equation for the falling object, right? So you drop something out of airplane, maybe yourself, right? With parachute, hopefully. The velocity going down is going to be initial velocity plus terminal velocity e to the negative kt over m minus the terminal velocity. That would be it. And are we done? We could be done, but this is a velocity equation. What else could we do? We can do it one more time and figure out the position, right? The height. 10,000 feet, 9,000 feet, 8,000 feet, 7,000 feet, right? So we can figure out the height because what is our velocity? It's change of position divided by time, right? So we're going to write that our velocity is dy dt, and then there is another separation of variables, where the only term that you have to worry about is actually that e to the kt. Everything else is a constant. So it looks insane, but now we can write dy dt is equal to v0 plus v tau e to the negative kt over m minus vt. Please, when someone asks what's new, bring it up, right? Say, pull the chair, right? Or if you're outside, start working it out on the napkin. It's good practice for the test, right?
Then people think I'm crazy.
No, then they know.
Are they not already now?
So when we separate our variables, we have our standard stuff. We're going to put this. We can use square brackets if you will, because now there has to be a dt in there, and we are going to hit both sides by the integral sign, and y equals, you know what?
You signed up for this. You brought this upon yourself. We could have just stopped after the first one.
Plus v tau t plus 1 over rho, so that's m over k. And then we have v0 minus v tau, 1 minus e to the negative kt over m. There we go. So this equation here gives you a position in respect to time. Scroll up for a moment. And hey, right? You need to see the equation, right? Yeah. That's what he said. Like precise. So the top equation up there is your speed, and the bottom equation over here, right? So this pair, body moving vertically under the influence of gravity and air resistance. Now that we're done with this example, you go back to the beginning of this example, and instead of velocity being proportional, you say, let's see what happens, because the Newton said it's the square. So now p equals to 2, and you repeat all of these calculations, right? So you go all the way to the beginning, right here. And instead of p equals 1, you say p equals to 2, and that's the next 3 pages. Scratch that, 4 pages in the book explaining what happens when the, right? No, 3 pages, 3 pages. No, 3 pages. Not bad. Same calculation, except now you have a kV squared, and you have to deal with that. So it might involve a little partial fraction decomposition here and there. Nothing that seasoned Calc 2 students can't handle, right? The book very conveniently skipped all of the calculations, just went and gave you the highlights. So you can try and hit all the targets as you go through. We are going to take a look at a variable gravitational acceleration. They have a flying saucer of some kind landing. And what I talked about earlier, this is the equation. I did mention this before, where the gravitational force drops off with a square of distance between the objects, which is why we are not all like clumped together as soon as we, are close. The reason why we are not leaving the planet is because we are way, way smaller than a planet in terms of the mass. So it looks like that we are attracted to the planet, but the truth is the planet is attracted to us as well. And anytime you jump, right, when you start going down, the planet also starts going up. But remember, when you jumped, you pushed the planet away a little bit, and then on your way down, you move the planet back, right, in the opposite way, so that both motions canceled out. So the planet actually didn't go anywhere. Well, actually it did, but in the net it did not. So that equation that is mentioned, obviously, and it has its own section, is F equals G mm over r squared. In physics, probably you might have a d in there. I know general physics was dragging d. R is better because radius. The gravity pool, when you want to represent the entire planet as a dot, the center of mass of the planet is going to be at the Earth's core. And then everything is going to be radially calculated from there. That's why you're going to also find the potential energy equation sometimes instead of mgh, mgr. Because if there is an object here, from here to there, it's r, and then usually we put that to be distance d. So when you overlook these things, some of your physics problems become very confusing. But understanding that from the center of the Earth to the height of the object, that it's something that you throw or something that it's falling down or whatever, right? The potential energy of that object, right, is converted into kinetic energy if it's moving, but it has to be moving towards the center of the Earth, unless there are side forces acting on it. But even if there are side forces acting on it, you will still do the triangle, decompose the force, and take the y force, which would be going towards the center of the planet, which in all cases is down, right? People on the other side of the planet right now, they're not standing upside down, right? They're right side up in their reference, right? Even though our feet are closer to their feet, right? And our heads are further apart, because they're right on the other side. Still. Anyway, so whether you know or you don't know that this G is 6.67 times 10 to the negative 11, let's call it good, right? And that's in the yes. 6.6, oh, show off, 2.6, okay, good. So they have 4 decimals, I have 2, I apologize. 10 to the negative 11 Newton meter squared per kilogram squared, right? That's the unit. Soft landing and the escape velocity. And sure, they ask you to calculate some of these formulas for homework. Well, I did one of them. So now the problem number 10, for instance, becomes very easy. It's just plug and pray, right? Because we already have all of the equations. Just give you the rho is 0.15 without the pair. So a woman bails out of the airplane. I don't know how they worded that, bails out of the airplane, right? Then you kind of want to continue reading and see what happened. At 10,000 feet, falls freely for 20 seconds, and then opens a parachute, right? how long will it take her to reach the ground? Assume linear air resistance, right? That's P equal 1, linear, right? And taking rho is 0.15 without the parachute and rho 1.5 with the parachute. So to solve a problem like this, right, you have the rho, you plug it in the equation, you just compute and you're done. There's no calculus to do. You are supposed to observe these problems where you actually first derive the equation, but I kind of killed all of that fun because it's already done for you, right? So you're plugging in the values, and I know, right? And you just plug the values in, and there you go. They give you the time of 20 seconds, and right, so if you read P is equal to 1, you have the rho. So just by, oh, there's the rocket propulsion problem on page 102. Ooh, so now it's no longer in the lesson. So escape velocity or the, yeah, we'll figure out something. And that's it. I hope you're not disappointed. No. Right? So we have these two major problems that we did, and if I assign the escape velocity, which I was leaning towards, but then there is a rocket propulsion one, which the escape velocity is the part of. And if you really want to learn more, if something like airspace engineering is something that might sound interesting, because with that, obviously, you can design airplanes and engines, but you can also work on rockets and so on. There's NASA, there's SpaceX, and so on. I strongly encourage you to take a look at a couple of courses that they have in the airspace engineering at MIT. All of the lectures are freely available to public. All you need to do is to, take a couple of hours to watch 28, 30 lectures at 1 hour each, I think, and learn about this. I remember when I watched that stuff like 15 years ago or so, the three engineers who actually designed the space shuttles back in the last millennia were the ones teaching the course at MIT. So these are the people who created the things, right? And they were teaching the course. Now, obviously, we all know that space shuttles are retired, but there was a step in our development of space exploration. So it's way worth. I mean, you have to know the old so you can improve and make better now. So it's important, and you can find them easily if you go just and type in MIT OCW in. OCW stands for Open Courseware. They have everything, all of the math courses, all of the physics courses, all of the chemistry courses, all of the video lectures, everything we learn here, and obviously way more. And you know that this school is like 60 plus a year, and you can learn everything now online like you were in a classroom. They also post homework assignments. They post exams, so you can see those as well. Go ahead into calculus exams and differential equation exam. Maybe that's how I can just print exam one. It's already done. I don't need to do anything. Wow. What an idea. Let's see who's not gonna actually do it now. Well, the curriculum is not gonna line up, but that just gave me idea to see, because the course is transferable. I mean, if you can't solve those courses, then right, there's an issue with alignment, I guess. So yeah, that's it. Bye.